So, hi, I'm Giulio Alessandrini. I work for the image processing team, part of the bigger sound and vision team at Wolfram. And I deal mainly with image color processing, both classical and machine learning, neural network based. And this talk is about the latter, of course. So first, I would like to set some naming straight, because while I was preparing for this, I noticed that there were a lot of names and that may be confusing for the same thing. So I decided to put this little piece of dictionary at the beginning, and which helps me clarify what we're going to talk about today. So many of you might be familiar with image classification, which is basically the task of identifying the main object in a picture. It's a kind of solved problem, quote unquote, in computer vision now. Like neural networks are performing very well on these. They can be very accurate and also reasonably fast. A closely related task is object recognition, which apparently is just like this kind of common assumed definitions, but it's not so important right now, I would say. But the point is, like, there may be pictures like this where you have more than one object, and you want to be aware of that. You want to realize that this is the thing. Then a bit more towards the goal of this talk, we have localization. That means that we want to produce bounding boxes for all the interesting, relevant, I mean, depends on the application, objects in a picture. And then finally, combining the last two steps, there's, and here the definition is a bit more agreed upon, object detection, which is the purpose of this talk. So the idea here is that I have an arbitrary picture, and I want to provide both localization and classification for each object. And usually, I also want to have a measure of the accuracy or confidence in this, how confident the detector is at this prediction. So how does this whole thing work? Typically, you have 3 steps in the detection pipeline. Also, stop me. Stop me. You can write at any point if you have questions. I'm trying to monitor the chart while I'm speaking, so don't feel that you have to wait till the end. Okay, so the idea is that we want a piece of software that will propose some region of the image. Then we want to convert these pixels into some sort of computable feature vector. Typically is a vector of features, but the idea is that we go to a tensor that represents semantically what the content of this piece of image is. And at the end, we want to take this and produce a classification. So, like, for example, this one doesn't contain anything. So what was the typical way to do this before neural network? I'm going to be very fast on this. The idea is, like, one basic thing is, like, why don't exhaust all possible regions? So you do something like this. You slide, and the region proposal step is basically sliding a window across the image, and you can do it. On an image pyramid, for example. So multi-scale. This is like making the window bigger or smaller, and this will allow you to produce candidates for theoretically all possible regions. You can vary aspect ratio too, and this is a bit inefficient because it creates a lot of boxes, a lot of proposals. So kind of a state of the art in classical image processing before deep learning was an approach called selective search, or like similar approaches. The idea is that you want to do a core segmentation, and then with the caveat that you don't want to split objects. Sorry, you want to split objects. You don't want to have one patch that spans multiple objects, and then you combine them to have some sort of region proposal at all possible scales. And this will create basically what you want to send to your feature extractor. So what are the feature extractors? Before deep learning, you had all sort of handpick features. One of the most famous is like hard-like features, named after the wavelets. The idea here is that you want to, for example, in this case, you want to subtract the pixel in the black area to the pixel in the white area, renormalize, and have sort of an idea of what's going on in a region combined, paired with the shape of the region. So the idea is that you would be able to, for example, here find eyes and nose, given enough descriptors. Other things you can do local binary patterns, or you can do deformable parts, like this use histogram-oriented gradients. The idea of all this is that you want to split your candidate box into sub-boxes, measure some property, do a histogram, and then send that to a classifier like support vector machine or something else. As you can imagine, this has all sort of problems, given the huge variability of pose, rotation, orientation of natural objects in images. And this was setting a hard upper bound on the accuracy of this classifier. So with the advent of neural networks, people started thinking, why not? I mean, this stuff is performing very well. We should actually use it for detection. So one of the first of these steps is this RCNN net that basically uses a standard region proposal with selective search, what I showed before. But instead of using classical image processing features based on filters or whatnot, it sends the part of the image to a convolutional neural net, which is creating the feature vector itself. After that, the feature vector is sent to a standard classifier. Like again, I think this model was using single support vector machines. So you have like one step replaced with the neural net. I mean, you do one, why not two? So there was sometimes after this, I think a couple of years after, a new model called fast RCNN, because it was also faster, that was only keeping the first region proposal part with classical image processing, and the rest was basically fully convolutional, fully neural net, let's say, pipeline. So you have you send the proposed image part to the feature extractor, and then you use these features to compute probabilities of classes and to regress the correct boundaries for the bounding box. I mean, we've done 2 out of 3. Of course, you can imagine that the final step was to do 3 out of 3. And so shortly after, this other paper came out, which is called faster RCNN, that is making use of the fully convolutional, fully neural net pipeline. I think this is maybe even fully convolutional. And the point here is that you use the convolutional feature extractor itself and the map that it produces to run a small network that is proposing bounding boxes based on the features. And then you send back those bounding boxes and you use them to mask this Roy pooling stage. It's used to pull out regions from the feature map. And then you slide. This is what it's called 2-stage detectors, because this is one net. And then you have a second net, which is this one, which has two heads, which predicts, similar to the one before, predicts scores and for classes and coordinates. And this network is light, so it's a map operation, if you're familiar with Mathematica, on the region proposed by the region proposal network. Here in this image, you see also one term which will appear again, which is anchor boxes. What does it mean? So the idea is that you are typically always better off having the network do the easiest job possible if you want like fast convergence, high accuracy. So the thing is, real objects, as I said, come in all sort of scales and aspect ratios. So the idea here was, why don't we help the network? Why don't we, instead of asking these heads here actually to predict the right center and the right width and the right height for each object, starting from no prior assumption, why don't we just maybe tell the network where the center was, like starting from which, I mean, the sliding window where it was, and also we give, in this case, K, 5, 6, 7, 9 priors on scale. You see, this is small scale. This one here is a bigger scale. These are 2 different aspect ratios. So basically, the idea is that if these are picked well enough, at least one of those will be very close or closer to what the actual scale and aspect ratio of my object is, and the network will have an easier job refining a good coordinates. So this is kind of has been a very relevant, and today still is a very relevant step. Okay, a lot of people were not super happy with this two-stage detectors. So there was a lot of research into like how do we make it, was it even possible to make a single stage? And for a long time, the answer was yes, but not with the same accuracy. So you had the detectors that can basically in one swoop, they predict features, and then they use those features to predict like not really dense, yeah, dense, let's say dense set of, like, you can imagine basically each one of these grids in these cells contains predictions, and so you're not sliding anything. The whole thing is the end of the convolutional pipeline, and you can just look at that, at what they are, and rescale accordingly. So this is faster because it doesn't depend on the number of boxes. The previous one had to slide, but was always suffering in terms of accuracy. So you have a lot of, you can see a lot of research into this. Like this is one network by Google, and you see that the idea here is to leverage more and more information in order to make these detectors more and more accurate. For example, this one here, I don't know if people know about this kind of model. Not of people know about deep learning here, so maybe I have to explain. The idea here is that you put the image in, and the image gets through a lot of filters that make it progressively smaller and smaller, and you read this going up, and they encode the information in the channel space. So at each time, you see this is the size of the image is getting smaller, and the number of channels of these images are getting bigger. You can eventually, I mean, in a classifier, you go to a 1-by-1 image with all the information in the channel space, but here, you just want to stay here. So this, then you can have these multi-scale predictions, and like they're pretty accurate. One last step, I don't want to spend too much time here, is like to get rid of the anchors. So there are models that are trying also to do that, to get rid of this last final step of prior knowledge in the models. So okay, we don't have much time, so let's have a look at how we can go from this kind of data to this kind of result. So let me tell you first, bad news. This stuff is not in 12.2. I mean, let's be clear. My own functions that I'm going to use here are not in 12.2, but good news, all the pieces that I'm using are in 12.2. So if you want to put up with the work, this stuff is trainable today. I mean, today, if you have a developer build, it's trainable today. Okay, this out of the way. Let's see what we can do. So I went online and I pick from Kaggle one simple fruit image detector. So it looks like this. You have test training folder, images for, I think, 3 types of fruits, and then XML files that contain the metadata for the detection. So the idea here is that we want to, let's see, here we have like a bunch of these XML files. They are saved with the Pascal Bock format, which looks like this. So this basically is a notation. I have my image, some metadata. It contains an apple, and this is a bounding box. But of course, I wasn't using that before. And the idea here is that we want to parse this, and I can probably provide attendees, if you're interested in this, I can provide you with these functions later. And this basically is to use to parse these VOC XML files into something usable by the Wolfram language. So we can do this for the training set, so we can do this for the test set, and basically then we have taken care of the data part. So then here, now we need to extract these features. We said we want convolutional networks to extract features from these images in order to produce boxes and probabilities. So here are a bunch of choices. For this talk, I wanted to start simple. So I said, like, let's try to do something which is doable entirely on my puny laptop. So here I'm defining, like, if you, I mean, I don't want to explain this stuff too much because there are plenty of talks in past tech conference that are available. The idea here is that you want to define blocks that perform convolutional operations, and you may use residual blocks, you may use squeeze and excitation block to basically recombine channel information. There are all sort of goodies that you can do. And then you want to put them together in a net that will perform this feature extraction one by one. So this is a network that ends in some classification, but you can always repurpose it for detection. So the idea here is that we take this network, and then we want to attach basically some layers at the end that will make it easy to read the classification information. So here I wrote some functions that basically does the job for you, and then it attaches layers for the YOLO architecture, and you just have to specify a bunch of parameters. And unfortunately, I don't think it scales very well here, but it takes the features and adds layers to automatically compute the parameters needed to regress classes and bounding boxes. And then the big thing, the big news is that now our framework is pretty much very pretty much evolved in the last version, is very solid, and is very easy to perform all sort of array operations on this, much easier than before. So I was able to easily write losses for a bunch of functions like centernet, YOLO, and I'm writing for more. So the idea here is that this is a very complex loss, and because you want to get inside, you have PCs, you have intersection of a union, like you don't want to waste too much time into this. I just want to spend 1 minute actually shout out to the neural network team that made this possible, and I'm sure that people, probably Jerome, are presenting this, but this is a neat piece of functionality in 12.2, and it basically allows you to take, like, this layer, for example. Here I wrote it to do the intersection of a union of two boxes with the same center, and this is a Mathematica function that you can just apply. And the idea is that now I can just take this function and put it in a function layer, and this will produce something that I can then use in this is basically a small parser that takes top level code, and when possible it converts it to neural network primitives. And together with this came lots of improvements that made the whole thing possible. So the idea is then not much more actually. So you take the old faithful net train, you put our fruit training set, you put the loss function, the test set. This I can, oh, what am I doing here? Let's do this. I probably don't want to train this real time. This is a couple of minutes. I just trained this before the thing. You see, okay, 1.3 minutes. I trained this before this talk. And oh yes, there's a question. I will put this notebook in the file section. Okay, so you can do object detection in 1 minute. Is it solved? Not really. So like it's not as simple as I'm showing this now. I mean, we can take this, and I wrote some more utility functions to just save up the hassle of doing post-processing. But then we can just apply it, and you see that not really good. I mean, this is a banana. It says there are 2 apples. Let's try another image. Okay, this is an apple. So I mean, it was going somewhere. Here's finding some apples, not all of them. So, I mean, it definitely learns something, but this is not the type of problem that you can solve in 1 minute. So, I mean, the setup was all there. So, what can you do to make this better? The thing is many things actually. First, you don't want to use a model that runs in 1 minute on a laptop. Unfortunately, this problem is still pretty hard. So you want deeper models. Some architectures that I showed at the beginning, efficient at ResNext, ResNet. I put this here so you can have a look. Some of them are already in the repository, but more about that later. So you want a model with capacity. So a model that has enough parameters to accommodate this task. You probably want to use multi-scale detector, which I didn't use for this short training. Here you had small apples, big apples. This stuff is never going to work there. And very important thing, lot of detection datasets are small. Is difficult to get this data. I mean, small compared to the task that you want to solve. So you absolutely want to do what is called data augmentation. So you want to generate more synthetic data from your detection data. This is also possible, of course, in the Wolfram language. You have wonderful image processing capabilities, and here I'm using one function to make it a bit easier, that is doing some flips, rotation, shifts, adding noise. And the idea is that you want something like this. Yes, if there's more noise or slight rotation, or let's see if I find one. Come on, it's 50%. Yeah, here, a flip. So all these are new images that generate more data that you can use for your training. And some of these are quite fast. You can use them online. Some argumenters, like if you want to do compose images, you want to change the white point. I mean, this can add accuracy, but maybe expensive. So you may want to pre-process your data before the training. And so I say I run a bunch of these things, and I still I wanted something that was trainable on a laptop. And then I created another detector that was trained in, let's say, half an hour on this laptop. Still not perfect, but you see, I can see which bunch more that banana was picked by both, apple was picked by both. The reason why these bunny models are not stretching is that really you need much bigger network that I can wrap on my laptop. So okay, for example, this one here, this is not picked up even after half an hour of training. Just to give you a comparison of the amount of time that you need, there are series detectors that are trained in a couple of days on multiple GPUs. So again, not a laptop problem. What happens if we take one of those networks? So this network here has never seen the image, but you can see that it has no problem in detecting that and in detecting multiple fruits at the same time. So the thing is, this is a problem that can be solved. It requires a little bit of care and right tools. And we are now working hard to make these tools available in the easiest possible way. So I don't know if we have little time to measure performance, maybe not. Let's talk about this a bit because it's more interesting. So the idea here is that this is a functionality that is coming. As I showed you now, I wasn't using anything secret to put together this talk. This stuff is all in 12.2. What I would like to add is a ton of quality of life improvements that will make this process much simpler for the end user. And for data parsing, data augmentation, defining all sort of loss, measuring performance. And the other piece here is that you always want to step on shoulders of giants. You always want to leverage all the time that was spent in putting together big data sets and training, for example, classification models. And to do this, we are constantly adding these models to the neural net repository. And I don't know if I can click on this. Oh yeah, it's open the other way. So let me go out of full screen here so we can see it. And where is Firefox? Okay, cannot find it on this screen. Oh, it's still on the other screen. Here it is. So this is a neural net repository. Models like EfficientNet are coming, and you can see if you go on classification, you can take some of these, like squeeze extension. You have MobileNet, and you can repurpose them very easily for detection. Another thing that I would really like to have is still in the easy of use direction, but to make both these instruments available individually and in a nice package. So my dream is that one day we'll be able to have something like this work, and that these days not too far away in the future. So we are really closing here. So thank you for your attention, and let me know in the chat if you have questions. I put the file in the file tab and clean it up a bit. Thank you very much to everybody. I'll be available if you even if you have questions beyond this slot. So just let me know. Bye bye, and enjoy the conference.